Okay. In theory, we're live. Let's see whether anyone is not at the moment. That's fine. We'll start in a minute or so. Hopefully everything is coming through okay. Just going to mute desktop and my audio a moment. Okay, experiment's over. I think we're pretty much ready to go. Let's get the right places. And hopefully you all can see my terminal. I'm not sure how quickly the stream works, what the latency is like, so we'll just have to deal with whatever it is. If anyone turns up, I will try to keep an eye on chat. Okay, so what is the purpose of this? The goal overall is to implement a logical puzzle solver. The sorts of puzzles that I'm thinking of are Sudoku puzzles, but also variant Sudoku puzzles, and pencil puzzles like Yin Yang and Cave and things like that. Basically ones that involve an ortholinear grid of cells and where those cells need some amount of filling in order to complete the puzzle. So if we look at an example of one of those, then this is a Sudoku puzzle, and in it we have 9 rows and 9 columns. Each cell can have one of 9 values, which are the digits 1 to 9, and there are also 9 boxes which constrain the grid as well. And from this, it's possible, in theory, I mean, I'm assuming that Sudoku.com wouldn't give us an impossible one, to complete this grid. So our goal is to write a piece of software which can do this. Now, there are a number of ways to achieve that, but what I particularly want to do is to write a logical solver. I've written just sort of guess and backtrack solvers before. They're very, very quick to write, and what they do is they'll tell you, yes, this puzzle has a solution, this is the solution, but what it won't tell you really is how would a human being go about achieving that solution. For example, if we look at this puzzle, then we can see that in this box here, which I would call box 4, then the 2s look in and they block off 2 from being in either of those cells, they block off 2 from being in either of those cells, so we know that 2 is over here. And 5 is blocked off from those cells, 5 is blocked off from those cells, so we know that 5 is somewhere here. So in fact we know that these 2 cells are 2 and 5. And it's those kinds of logical deductions that we would like to see a solver actually give us. Now, to achieve this, we're going to have to write a lot of code. My intention is to write this code in Rust. I'm going to attempt to make it understandable, and certainly if anybody is watching along and asks questions, then I will try to explain them. In this stream, my hope is to get something working for very basic puzzles, and overall to extend over time to have much more complex solutions to support variant Sudoku constraints and that kind of thing. I'll just give you an example of variant Sudoku constraints. So sorry about the very bright colors for a moment. Let's pick a nice easy one. Unfortunately, Sudoku Pad is bright as well. And I don't think it has a dark mode. Let's just have a little look. Anything in experimental? Ooh, an alpha dark mode. Ugh, that's really not very good, is it? So let's not do that. But this is an example of a variant Sudoku puzzle. So here we have a 6x6 puzzle rather than a 9x9. And in this puzzle, you can see these cages. And these cages have a number in the top left corner. And that gives an indication of what value the digits within those cages have to sum to. In addition, digits can't repeat in cages. So even though Sudoku rules would allow that digit and that digit to be the same one, because they're in the same cage, they can't be. And it's these kinds of constraints that I eventually want our solver to be able to deal with and to be able to give us logical conclusions for. So step one in any kind of generation of software is going to be to name it. Naming is probably the hardest problem in computer science. So let's begin. I think I made some notes, and I've been thinking about names for this, and I thought about solvents like toluene and acetone. I like to give things silly names, but I've also of late started to use people's names where the person has something to do with the sorts of things that we're dealing with. So I thought maybe Lewis Carroll is a good name. You know, we could call the tool Lewis. Lewis Carroll liked to set logic puzzles. And then there's Howard Garnes, who is often credited with having set number place, which is kind of the initial foray into modern Sudoku. Or there's Kaji Maki, who is the Japanese person who first called it effectively Sudoku. And they were the president, I think, of Nikoli Puzzle Corporation in Japan. So my leaning is towards calling it probably Kaji. So that's what I'm going to do. So let's call it Maki Kaji or Kaji Maki. Let's just call it Kaji. And what I need for this is all of the basics for a Rust project. So before I begin, I'm going to grab now I run Nixos, so I'm going to grab out of one of my other projects what's called a flake file. And this is one for my journaling tool. So we're going to call this Kaji, a logical puzzle solver. And just very briefly do that. And I don't need a post install because we're just calling it Kaji. So there we go. And use flake. Right. So all that basically lets us do at this point is that I know I can run build tools and so on. So let's do that. Let's thought. I'm probably going to end up with multiple crates in this repository. So let's cargo new -- bin Kaji. And let's cargo new -- lib. Tell you what, let's make Kaji bin and one called Kaji, which will probably be like the core library. We may end up with the solvers and other things as well. And then let's create a top level cargo.toml, which just covers those two crates. Trying to remember how I set a default crate. Do I do that in cargo.toml for that one? No, because Juntakami is at the top level. Let's find out. Cargo default crate. Default members. No, that isn't right. What do we do? What do we do? In the workspace case, the default run belongs in the top level toml file. So if we pop over here, I mean, that's running the code. Tuesday edition 2021 resolver. Specify resolver equals 2 in the top level manifest. Let's do that. Unused manifest key workspace default run. Okay. What is it that we need? Cargo.toml workspace default. It's default members. Okay. So the default members will be the program. And we'll tidy that toml file up before we do anything else with it, so that's fine. But now we're definitely just running catchy bin, and when I run cargo test, we're just running it there unless I run --all, in which case we run it everywhere. Excellent. We do not want the target being there. We don't need the direnv. I think that's probably it. Let's grab ourselves a license. I'm going to use MIT because I think that's reasonable. I'll worry about setting up the SPDX entries in the cargo.tomls at a later date. So I think we're ready. Let's right, we have our initial commit and we're ready to go. So let's bring up a code editor. I'm afraid I'm how can I put this? Boring these days. I know a lot of people have fancy text editors like NeoVim with all sorts of plugins and what have you. I'm not dealing with that, so I'm afraid I'm just using VS Code. You can rib me in the comments. But for now, let's begin by thinking about what it is that we need to be able to do. We need to be able to give Kaji a puzzle and have it give us the solution. Or rather, both the solution and the way it got there. So we need to work out a way to encode a puzzle. We need to work out a way to encode the rules. And then we need to get somewhere with that. I said that we'd probably use Kaji, the library, to be where we're going to store the main types, the main puzzle types. So things that I have thought about for this are that I want a division of what it is to describe a puzzle and what it is to have a board state for a puzzle. And part of that is that having fully described a puzzle, that realistically could be read-only. But even if it's not, we might want to sort of store a board state so that we can store all of the board states in the logical path to the solution, even if we're mutating the puzzle data as we go, as we learn things, for example. So I'm imagining, and let's say Kaji is a puzzle solver. Give me one moment. Being pinged. Right, where was I? Yes, so we're going to say Kaji is a puzzle solver, and we'll just leave it at that for now. I like to make sure everything is documented. In practice, I'm not going to be terribly strict at the moment, but eventually I want to make sure that we have good code documentation for this, because one of my goals here is that it should be reasonably easy for me to teach it new constraints, providing I can program the constraint, obviously, in order that as I develop new puzzles, I can teach it the constraint and then have it show me how a human would solve the puzzle. So I can make sure that I've not created a puzzle that, while theoretically unique, is in practice not something a human being can solve. And to me, a human being is effectively anything that I can successfully program. So, if I think that it's reasonable for me to program a logical step that randomly picks an answer and then forks the board and tries to work the solution out, then fine. Except I don't think that's a fair thing to do, so I'm not going to do that. So I said we're going to have a puzzle. So let's have a puzzle. And for now, things that I know I want the puzzle to be able to do is I want them to be clone and I want them to be debug. Because that way I can dump the puzzle out if we're confused as to what's going on. And I can clone the puzzle if I feel that I desperately need to, although maybe I'll get away without clone for now. Let's just go with debug, because I do want to be able to debug print the puzzle. Remember that a puzzle is the setup, not the solve path. I said when I was describing puzzles, if we come back to this example of Sudoku, that it's an ortholinear grid of cells. So that means that puzzles have a width and height. And therefore every cell has a row and column coordinate. I did consider what it might be like to say, actually, I would like for every cell to potentially be in an arbitrary location. And so I feel like while I'm going to have a grid, there's no guarantee that every row column combination on the grid has a cell in it. There are some puzzle designs that, for example, deliberately have cells omitted from the puzzle. So we're going to have a width, and I'm going to make that a U size, and we're going to have a height, which is a U size. So this is the overall grid size. No coordinate can exist outside of that space. But what human beings think of as coordinates is not necessarily what the puzzle system thinks of coordinates. So maybe actually we don't need those. I'm going to get away. I'm going to say we don't need those for now. But what we do need are symbol sets. And Sudoku has one symbol set, which is those digits 1 to 9. But we could quite plausibly end up with multiple different symbol sets. So let's think about symbols for a moment. A puzzle cell symbol. Pub struct symbol. We should probably make that debug. So symbols to me are things like, the digits 0 to 9 or 1 to 9 in this context. So for now, we're going to have a display, which is a string, because we need to know how to show that that symbol is present. And do we need a value? Let's just leave it at that for now. So for the moment, symbols just have a display. And then we need symbol sets. a set of symbols in a Sudoku puzzle. And I'm actually going to add a little bit more flavor text to this. So cells can ultimately have only one symbol present in them per symbol set associated with the puzzle. So a symbol set is a collection of symbols of which exactly one can be present in a board's cells. For example, Sudoku has 9 symbols, the digits 1 to 9, but a Sudoku yin yang hybrid puzzle has 2 sets, the Sudoku digits and a set of dark/light. So, as I said, my hope is to be able to use this for other kinds of symbols in the future. So we're going to support having multiple symbol sets, and we're going to allow for a cell to have a symbol from each of the symbol sets in the puzzle. Right now, we're probably only going to do a single symbol set, which is the Sudoku symbols, but maybe in the future we'll get to the point of implementing these hybrid puzzles. Is anyone asking anything? Let's have a little look. No, chat still looks quiet, which is fine. So let's carry on. I'm going to say... So, I've been doing a lot of research, and I will show you some of the stuff I've been doing research with. But one of the things that I've noticed is that in Rust, we can do a lot of bit manipulation as long as we're using relatively well understood integer primitives. And U32 is a pretty good integer primitive for us to be using as bit sets. So what I'm going to say is that for ease of implementation, symbol sets will be limited to 31 symbols per set. This allows the available symbols to be represented as a U32, oopsie, leaving 1 bit available to say the cell is solved. And this just happens to be a common optimization that's in place in solvers. So we may as well take advantage of that. So a symbol set is going to have some symbols, which will be a vec of symbol. Should we give it a name? We'll give it a name. And we will derive debug on it, which is probably going to complain. No, we did that symbol as well. Right. So symbol set is going to be, and symbol are going to be our core types for dealing with the contents of cells. So puzzle is going to have symbols, which is going to be a vec of symbol set. And we're all good. Right. So other things that we know that puzzles need is puzzles need the constraints that are being applied to them. So we're going to have a go at some of that. So let's actually do a little bit of tidying up of the code. Let's make a symbol module. And let's move all of that into the symbols module. Let's create a puzzle module. I'm gonna just do all of these as pub crate because I just want to be sure that we're good. and going to use create symbols star here just to pull that type through. This is just so that as we start to add implementations to all of these types, it's going to be less of a pain. So I said constraints. So let's talk about constraints for a moment. So constraints are something that restricts the grid in some fashion. So if we look again at Sudoku, there are three constraints in place, and they're all related. And the constraints are this. We already have a definition of a puzzle which says that every cell in the puzzle, and at the moment we don't know how many cells there are or where they are, but we know that there are cells. We know that every cell in the puzzle must, when the puzzle is solved, have one symbol from each of the symbol sets in it. Sudoku adds the rules that every row, every column, and every 3x3 box must contain one each of the symbols. So there is a row constraint, there is a column constraint, and there is a box constraint. A lot of puzzles have these kinds of constraints. Sudoku calls these things houses. The rows, the columns, and the boxes are houses. Other things maybe call them regions and things like that. So what we're going to do is we are going to have a kind of constraint, which is effectively this set of cells cannot contain repeats. We'll call it something like a non-repeat constraint. And then we can feed it all of the rows, the columns, and the boxes. And then, that will give us quite a lot of the functionality that we're looking for. Right, so to that end, we need to talk about constraints. Constraints are clearly going to be traits, because we're going to have lots of different constraints and we're going to have to manipulate them through a trait in order that we can have something reasonable to deal with. So we're going to be looking at pub trait constraint. And what do we know about the constraint? We're going to say that it has a... So every constraint when constructed, we're going to be able to hand it to the puzzle. So for now, I'm just going to do that. And we're going to come back to the puzzle and we're going to use create constraints star. And we're going to say that there are so we're going to say that every constraint ultimately is boxed. So we're going to have a boxed in constraint. Din constraints constraint plus tick static does not implement debug. So we're going to have to pop back to here and we're going to have to say that you always have to implement debug in order to implement constraint. So it's a bit grungy, but we're going to say that. You always have to implement debug in order to implement constraint. This will allow puzzle to continue. We'll worry about writing code in for constraints later. We need to continue to think about how we're going to build our puzzle. So I've said at the moment that we don't actually know where the cells are. So let's fix that. We're going to need some cells, and they're going to need, well, what are they going to be? So a cell is a place on the board. It can have some value. Those values are symbolic. Each cell has one value per symbol set. Cells have coordinates. So that means that there's rows and columns. Do we want to have a complete grid, or are we content to have any set of cells with rows and columns? I think that we should allow for almost anything. So we're going to have a vector of cell info. And a cell info is going to be information about the cell, like its position and what have you. So let's pub struct cell info. That's going to have to derive debug. So let's think about, what does a cell have? I said it has a row and a column. Other constraints are then going to introduce other information which could be considered coordinates. So, for example, Sudoku has boxes, and those are considered important. So I'm going to say region. I'm going to say region because there is such a thing as an irregular Sudoku where the boxes aren't 3x3, but they are considered equivalent to boxes. So we're going to have a region number. Actually, does a cell always have a region number? Not always. Think that if we're just doing a Latin square puzzle, then Latin squares just have the row and column uniqueness constraints. They don't have regions. So let's leave it for now at saying that a cell has a row and a column and it has a name, which we're going to, again, make a string. And the reason that we want to say that it has a name is because we want to be able to give each cell a name so that we can refer to it when we want to print out logical information. It'll probably be row 1, column 1, that kind of information, but we definitely want to be clear about individual cells' names. We have these regions, and I said that regions are important in these kinds of puzzles. They often have no repeat constraints in them, but also many rules like to talk about regions. So, for example, Sudoku likes to say that a region must have one each of the symbols in it, and so the constraint that is building that would want to know the regions in the puzzle. And regions could be, a full set of symbols. They could be bigger than a full set of symbols. They could be smaller than a full set of symbols. They're just a sequence of cells. So we're going to have regions, and regions, we're going to have a vector of, and I'm going to say cell index. And the reason that I'm saying that is because we need to be able to refer to these cells over and over again in puzzles and in boards. So let's talk about cell indexes, which are effectively going to be indices into this particular vector. So it's actually a vector, let's actually call it a vector of regions, and let's derive debug on a region structure. And the region structure will have a name, and it will have some cells, and the cells will be a vector of cell index. And let's derive debug and talk about cell indexes. So what is a cell index? Well, we said it's just going to be an index into the set of cells here. So what we're going to do is effectively it's going to be a new type over usize. And we're going to do that so that we can't accidentally pass the wrong things in, because we're probably going to talk about regions by region index. So let's do that, region index. And when we talk about symbols, we're going to have symbol set indices, we're going to have symbol indices, so that we can look these things up. Yeah, I think that's fair. Okay. So, I mean, all of this is just complaining about construction. That's fair enough. What else do we need to represent a Sudoku puzzle? Bearing in mind we're representing the puzzle here, not the boards as we go through solving. I think another thing that we need to represent here are the constraints themselves in terms of how they restrain values in cells. One thing that's really quite clear to me is that a lot of Sudoku constraints can be represented as simple inferences, or sort of mathematical implications. And what I mean by that is that you might have a rule that says one of each symbol in a row. That rule is effectively saying that if you have a 1 in row 1, column 1, you cannot have a 1 in anywhere else in row 1, you cannot have a 1 anywhere else in column 1, you cannot have a 1 anywhere else in box 1. So those are if A, then not B inferences. So I think we want a way to store that. Now, I have spent a lot of time speaking with Ranksk, who is quite famous in the Sudoku world for their work on Sudoku solvers. Their solvers do all sorts of clever stuff with backtracking and brute force solving, which we don't want to do. And it's more fun to implement for ourselves. And what they do is they have this implication mechanism in place. I think they tend to call it weak links, because if X then not Y is a pretty weak logical implication, but it's pretty powerful as well, because if you can say that if cell A contains value B, cell X cannot contain value Y, then you can also say if cell X contains value Y, then there's no way that cell A can contain value B, because that would be a contradiction in the puzzle. So anytime that you add one of these weak links, you actually get to add multiple of them. But this means at this point that we are talking about, for a given cell, the existence of a given symbol in a given symbol set precludes the existence of another symbol, the existence in another cell of another symbol in another symbol set. So we need to have a symbol ID, which I think realistically should encode both the set and the symbol number. So let's add that type as well. So a symbol ID, and I'm going to say it's a usize, and the reason I'm going to do that is because what I'm thinking here is that that's going to encode it by offsetting, because we said that there's a maximum of 31 symbols in a set. So if we take the symbol set number and we shift it, then we can encode the symbol within the set in 5 bits. And so I think it's reasonable to say that there will not be what could amount to like 25 bits worth of symbol sets. So we'll do that. In fact, let's make a note to that effect. A symbol ID encodes the set and symbol. Internally, this is represented as the bottom 5 bits being the symbol index, and the next 5 bit, and the rest being the symbol set. So having said that, we can now say that an inference is a particular cell, which we have cell indexes for, particular symbol, inferring not a particular symbol in another cell. I'm going to stick repr transparent on these just to make damned sure that we don't accidentally fluff anything up. So let's talk about our inferences. Inferences. Do we need anything clever here? We could just do hash sets. Let's just do hash sets. So what we're going to do here is we're going to bring in the hash map, and we're going to say what do we want to call these? I mean, like I said, Ranks calls them weak links. I know that in their JavaScript solver, someone else has implemented like all the different kinds of implications. But I think the basic negative implication is fine. So let's call them implications. And it's going to be a hash set where the key is a tuple of cell index symbol ID to cell index symbol ID. And hash set is probably going to complain at, sorry, it's a hash map for a start. And because we're repr transparent, I think it's happy to do that because cell index and symbol ID are hashable. Okay. Right. We have implications, we have cells, we have regions. I think it's theoretically possible at this point to begin to construct a Sudoku puzzle. So, do I want to move any of this stuff out for now? I'm content for this to remain in puzzle.rs. Let's go back to main and let's think about what it means to construct a Sudoku puzzle. So we're going to have let's assume for a moment that we can do that. And we're going to do this by doing use kaji. Puzzle. And we're just going to expose things like that. So now we have a dependency which says that kaji comes from kaji. And now puzzle is not exported. That's okay. Pop use puzzle. In practice, we're going to end up creating like a prelude module because we're going to need to be able to import all sorts of things, but that will do for now. And then that's going to go, there is no puzzle new. Do we want puzzles to have names? Probably not. I think that's fine. So let's have import puzzle. Now, do we want new? Or given that for now we're only going to be doing Sudoku grids, shall we say new Sudoku? Let's do that. Pub fn new Sudoku. And we're going to say, what is the size? So, yeah, size, which will be a U size. And it's going to produce a puzzle. And what this will do for us is we can just pre-initialize everything trivially so that we can get on with trying to do other things. Okay. So we're going to return a self. And what's it going to contain? It's going to contain all of these things. And now we can come back to Kachi Ben and we can go new Sudoku. Do we want to do a 9x9 or a 6x6 first? Tell you what, let's look for a classic 6x6 Sudoku. It's got to be one. Here we go. Oh my goodness me, I'm terribly sorry. Let me fix that. Right. Okay, so this is a 6x6 Sudoku, and it should be easy to do. So let's assume that this is good. As you can see in a 6x6 Sudoku, every row, every column, and every 3x2 box has 6 digits, and the digits are 1, 2, 3, 4, 5, and 6. Let's assume for the moment that we're always going to do a 6x6 Sudoku. So we're going to pass 6 in, and then it's going to say, hey, we're not using this, so let's go. And let's print out the puzzle, and of course it's saying at the moment it doesn't need to be mute, so we'll get rid of that for now. So we are creating a 6x6 Sudoku, and again, we're going to hard code this to be a 6x6 Sudoku. I really don't want to do anything clever at the moment. We're just bodging it together. So we're going to assert that size equals 6. So we're only supporting a 6x6 Sudoku. So let's build the symbols that we want. So symbols are a symbol, well, it's a vec of symbol set, which contains name, which is going to be the Sudoku digits, and symbols, which will be a vector, and each one will be a symbol which contains the display, and am I allowed to do that? The name symbols of struct symbol sets is private. Haha. So immediately we need some extra information. So let's pop across the symbols and let's write an impl symbol set pub fn new name. In fact, let's take an impl into string there, just because that might be what we want. Do we want to take a set of symbols already? Yeah, why not? So then you're going to create a symbol set. You need... No, we'll push the symbols in. Why not? So that produces a self, which is going to be name and that. And then we're going to need symbol push, and that's going to take this. Well, it's going to take a symbol, which is impl into symbol, and it's going to take a borrow mute self to cope, and it's going to return the index of that symbol in the set. At the moment that might not be relevant to us, but later it might be, so we may as well return it. No, I'm going to stop doing this. I have a tendency of like going, oh, I'm going to want this in the future, and even at the moment with all of the stuff I've put in for thinking about the future, I can't really think about anything that I would want that for yet. So let's just push the symbol in for now. We can write iterators for symbols later. So we're just going to go self.symbols.push symbol.into. Okay. Let's write an implementation for symbol. Pub fn new display. So that, and then I'm going to write an impl into a symbol for borrow. Well, in fact, can I do this? Impl s into symbol for s, where s implements into string. And we can just do symbol new self. Is that allowed? The type parameter s must be covered by another type when it appears before the first local type. Foreign trade thing possible, blah blah, type is local. Yeah, I'm not allowed to do that. curses. Let's have a think. Let's just do into S4 string. An implementation of from is preferred. From string for symbol. Okay. Ooh. Does that mean that I could have done impl no, because it would have been impl s from s for symbol, which would still have been the same level of not right. And let's impl from that as well. Okay, let's come back to our puzzle. So now we're going to need some symbols. And that's going to take the name, which is going to be digits. And we need to push all of the Sudoku digits in. And then we're going to be able to say that that just is symbols. And let's rename that. 1, 2, 3, 4, 5, 6. 2, 3, 4, 5, and 6. So we've created our symbols. That's reasonable. I don't think we want any more than that. We said that cells always had a row and a column. Do we want a lookup table from row column to cell index? I think we probably do. So let's go row cols is going to be a hash map from cell from u size to cell index. Alternatively, we could just always say that we have a complete set of cells. Come on, make a decision. No, I'm going to force myself to cope with an incomplete set of cells, just in case, because that sounds more interesting. Okay. The constraints for now are going to be empty. So the cells matter. It's going to be a vector of cell info. So let's do this. Let mute cells vec new for row in 1 to 6 for col in 1 to 6. Name. Name is that, and then cells push. We want to push a cell info, which has a name and a row and a column. And we also need to prepare our row cols structure. Let mute row cols equals hash map new. Row cols dot insert row comma col comma cells dot cell index I mean, again, we're constructing this stuff really, really dodgily at the moment, but that's fair enough. So we're saying that we have our 6 rows, our 6 columns. The cells exist in those rows and columns, so we can work from there towards what we need. So our next step is going to be to build the regions. So what are the regions? In 6x6 Sudoku, the regions are effectively the rows, the columns, and the boxes. So let's go for n in 1 to 6. Let mute regions. So let's make the rows first. Region equals region. Name is going to be row n, and the cells are going to be all of the cells that are in row 1. So they are going to be row cols dot iter filter given a key and a value. Well, actually, what happens? So it's given a borrow of the coordinate to there. So what we actually want to say is that we're going to remove that borrow, and we're going to say that what we have is we have row column. Sorry. We then have a borrow of row and column and a cell. I think that's fair. And what we want to say is row is equal to n, then we want it. And in fact, what we can do is filter map we can say if row is equal to n, sum cell else none, and we can collect. Right, how close are we to doing something that's possible? Mismatch 2 expected a borrow usize, borrow puzzle cell index. Found a borrow. Okay, so it doesn't like me destructuring like that. For whatever reason. So it's v dot 0 dot 0 is the row. Then we're going to return v dot 1 dereferenced. And now it's going to complain about various things. Let's pop the semicolon there. We're going to go regions.push region. We're getting closer. It's going to complain that we cannot move out of that because it's a shared index. So I think it's fair to say that all of our indices are, in fact, clone and copy. And so are our symbol IDs. Because that is vaguely sensible. Let's rename that as row region. And let's repeat that for the column regions. And it's going to become column n, and it's not v.0.0 is v.0.1 for the column, because it's always row, comma, column. So there are our row and column regions. Those regions are Latin square enough, but now we need the box regions. Can I think of a nice, neat formula for making the boxes? Not really. Can I hard code them? I mean, effectively, we want row 1, 1, 2, 3, row 2, 1, 2, 3. That's box 1. So it's always... So if region 1 is always row 1. Region 2 is always row 1. Region 3 is row 3. So that given a region number, if we subtract 1 from the region number and then divide by 3 and then add 1, we get the row number. Yes. Oy, okay. Boxes are a bit more of a pain. Let box row equal n minus 1 divided by 3 no, silly. Boxes 1 and 2 are on row 1. Boxes 3 and 4 are on row 3, and boxes 5 and 6 are on row 5. So if we subtract 1, knock off the bottom bit, and then add 1. So if we go n minus 1 and not 1, plus 1. So that should be the box row. Box col is going to be 3 times n and 1 plus 1. N minus 1 and 1 plus 1. I mean, this is all hideous, but, you know, we'll get somewhere. So let's stick our semicolons in. In fact, let's just prove to ourselves that we're doing the right thing. So we can say box n starts at row, column, box, column. And for now, let's say that we don't have any implications. So the regions are going to be the regions, the implications are just going to be the implications. Implications are a hash map. So if we just run that, all that debug output. So row 1, column 1, row 1, column 4, row 3, column 1, row 3, column 4, row 5, column 1, row 5, column 4. Those are the box starts. Excellent. So each box is always 3 cells from box row starting at box col, and then 3 cells at box row plus 1 starting at box col. So let mute box region equals region name box n cells empty vector for row in box row dot equals box row plus 1 for col in box col dot equals box col plus 2 box region cells push row cols get box row box col. Get is going to return a borrow, so we can dereference that to copy it. Regions push box region. What's going on here? Oh, get. Actually, what we can just do instead is that. That might need to be a borrow. Yeah. We know it's going to be fine. Yes, in theory that could fail, but in practice it's going to be fine. And it's not box row and box col, it's row and col. So, if we run again, let's see if we can get... So for example, here we can see in row cols that row 2, column 1 is cell index 6. So if we find row 2 or column 1, or box 1 for that matter. So row 2. Interesting. No, it's box 2, sorry. Row 2, column 1 is cell index 6. Box 1, index 4 is cell index 6. Row 1. No, so it was row 2, column 1, didn't we? Excellent. And if we find the 6th entry in this list, 1, 2, 3, 4, 5, 6, 7, because it's 0 index, then we have row 2, column 1. So we can be reasonably confident that we've constructed all of that except for the implications. And we're good. Woo! Goodness me. Okay. So implications for Sudoku are that for every region, each cell must be unique. There's the phrasing. Goodness me, that was tough. Okay. So, let's have a think. For region in regions. For cell. In I mean, realistically, what we want to do is we want to double loop at this point because we want to say that we are going to set up the pair of inferences for those regions. I mean, if we're willing to say that a region, if it is equal to, well, if it's present, always implies a uniqueness, then we could write a helper function for it, which might be a bit more reasonable to do. Let's say that regions always imply uniqueness, and then let's write a helper function, because otherwise it's going to be a pain. So we're going to just have a blank set of implications, and then we're going to create the implications by iterating the regions. So for region in ret. Ooh. How we want to do this? For region index in 0 to ret.regions.len. For cell 0 in region in each region, we know, I'm really tempted to just say each region is. What do I want to do? I'm going to say that let's actually start to build up some of the helper functions that we're going to need. So we're going to have regions self, and it's going to return a region iter. Self.regions.len. Right. So it's going to return a region iter, which is going to be an iterator over regions. So let's do that. Which has a count, which is a usize, and a pos, which is a usize. In fact, it's going to return an impl iterator item equals region index. And what that is going to be is it's going to be 0 ... self ... regions.len .map region index. And hopefully, because there's no need for like a plus tick underscore, so there's no borrow coming out in that iterator, we're good. So we have something that gives us region indices. Cells for region, which takes self and a region, which is a region index, and it returns an impl iterator where item is cell index. No. We're going to have a region which takes that, and it gives you back a borrow region. just because you might want the name or something else. So let's do that. So this returns borrow self.regions like that. And now let's do an import region cells, which takes borrow self and returns an import iterator item equals cell index. And again, I'm deliberately trying to avoid the borrows here so that we can be moderately confident that we can come back in and we can edit the puzzle and so on later without hitting, oh, you've got a borrow of that, so you can't have a borrow mute and so on, because partial borrows don't happen yet. And we're storing implications next to regions because we want to, but we want to be able to build these things up over time. So that's fair. So asking for the cells is going to be expensive because it's going to be self.cells.clone.into iter. So that's expensive. So I'm actually going to call that clone cells. No, because clone is thingy. We'll call that cells, and no, we'll call that 2 cells. Because that's the implication that it's expensive. So that gives us cell indexes. So if we're going to do this, we're going to say for region in self.region, not self.rect.regions. So that gives us our region index. We're going to say for cell in region, ret.region region dot to cells. That gives us a cell index. That's cell 0. For cell 1 in ret.region region dot to cells. Actually, what I want is every pair of cells. And I've converted that to an import iterator. Perhaps I should convert it to a vec. So I should just return the clone of the vector. I'm going to do that. So I'm going to say that actually that's that. So that I can say cells is ret.region region dot to cells. And then I can say for cell 0 in 0 to cells.len minus 1. Cell 1 in cell 0 plus 1 to cells.len. So we've now got every pair of cells. And what we want to do is we want to say for every we want to say these two cannot be the same. So mark different. So what I'm going to do is I'm going to go ret.mark or different, infer different. Cells, cell 0, cells, cell 1. And let's write that. Pub fn infer different, which is going to take a borrow mute self. It's going to take a cell 0, which is a cell index, and a cell 1, which is a cell index. And the job of this is to say, okay, whatever's in cell 0 can't be in cell 1, whatever's in cell 1 can't be in cell 0. And that's essentially doing the same double loop, but with inferent, with the so for each symbol set, Should we do it for each symbol set or just for one symbol set? We'll just do it for one symbol set. I mean, this is all hacky for now. We're going to assume there's only one symbol set, so we'll just do it for the first symbol. We'll do it for all symbol sets. We'll assume that if the symbol set has the same number of symbols as a region, but we don't know what region we're talking about at the moment because we're talking about cells. Okay, I don't want to do this as a function yet. Let's continue to do it in here. We already know that we're talking about symbol set 0, symbols 0 through 5. So let's write an implementation of symbol ID, which has a pub crate new, which takes a set, which is a usize and a symbol. Actually, no, let's do that. Do we have, so we have a vec of symbol set. Should I have a symbol set wrapping that? No. What I should have is an impl symbol set fn to IDs, which takes a borrow self and a set number and gives back symbol and impl iterator item is symbol ID. Okay, let's do let digits equal ret dot symbols 0 dot to IDs 0 dot collect in a vec. So we're going to get the digit symbol IDs, and to do that we want to say that this is 0 to self dot what does symbol set wrap? Let's have a look. Well, we should be implementing it over there anyway. Okay, let's fix that. So coming into here in symbol set, self dot symbols dot len map right, we need to move symbol ID from puzzle. Over into symbols. So we can do symbol ID new set comma s. And then we can import symbol ID, which just has a new function that is not public, that takes a set and a symbol and gives back self, and it's going to be self brackets set shifted left 5 or symbol and 31. So that forces the set and symbol ID. ret.symbol 0.2 IDs is private. So we can make that public. What else are we missing? We should move. And we're probably good. Okay. Let's keep going. Goodness me. So we have acquired our digits. So what we now want to do is we now want to say, we've got for each pair of cells, we want to say for each pair of digits, or rather for each digit cell 0 has, for each cell 1, it cannot have that digit. Yes. For digit in digits, ret dot add implication. So it's cell 0, that digit, cell 1, that digit. And we can, in fact, we could do that directly. So we've said implications are, if the source cell has that digit, the destination cell can't have that digit. So we can construct these directly, but let's push the inference in so that we can do the inversion. So we're going to say ret dot add inference cell 0 digit cell 1 digit, and let's write that function. So pub fn add inference, which is going to take a mute self. It's going to take cell 0, which is a cell index. It's going to take has, which is a symbol ID. It's going to take cell 1, cell index, lax, symbol ID. And the idea here is that we are inserting that inference. So this is saying if cell 0 is has, cell 1 cannot be lax. Corollary, if cell 1 is lax, cell 0 cannot be has. And that's, yeah, that trivially holds in the sense that if cell 0 is 1, means that cell 1 cannot be 2. Then if cell 2 is 2, we know there's no hope of setting cell 0 to 1, because that would introduce a contradiction, because it would try to eliminate 2 from cell 1. So we can insert both ways round into our hash map. So we can say self.inferences, no, implications, insert push. How do I insert into a hash map? I'm pretty sure it's .insert. And we're saying cell 0 has, cell 1 lacks. What's wrong? The method insert exists for hash map, but its trait bounds are not satisfied. cell index does not do equal. Aha! So just because we said they were transparent, we managed to construct the hash map, but we couldn't actually do anything with it. Let's complete here first. Arguments, this are incorrect. Let's try and get rid of as many errors as we can in turn. Right, so now we know that cell index has to implement partial EQ. EQ. Ordering doesn't make sense for cell indexes because what does it mean for one index to be less than or equal to another? And we almost certainly need to implement hash. Now what are we missing? Symbol ID. So again, I think partial EQ and EQ is fine, and hash. Okay, and all of our implications in theory are present now. So if we cargo run, I think these are all of our implications. These are saying like cell index 31 symbol 2 means that cell index 35 cannot have symbol 2. Perfect. So at this point, we've, I think, successfully initialized a 6x6 Sudoku grid as a puzzle. We then need to put the givens into the grid in order that we can proceed. Givens are, I suppose, a kind of constraint. Or they're a rule. So, but we can only apply those when we have a board. So we've applied all of the implications that we can. We now need to prepare a board and then apply the given digits to it. Okay. We're getting somewhere. So let's create no boards. I mean, I've been calling them boards. Maybe I should call them grids. I don't know. It's another type. Let's stick it up here for now. I'll call it board, but we might name it something later. So a board is the cell state of the grid during a puzzle solve. For example, it will contain the found digits and the results of any implications they have. It is meant to be moderately cheap to clone. So every cell in the board consists of what? A U32 for each symbol set the cell could have. And do we want to say U32 or do we want to say it is a symbol choice? I'm going to say it's a symbol choice. So it is a vector of symbol choice. And we can probably put that into symbols into here as well. So a symbol choice is a U32 which represents which symbols from a symbol set a given cell could have in a given board. No, I don't like this being a separate type, and the reason I don't like this being a separate type... No, that's okay, because it's for a given symbol set. So that means over here, when we talk about a board, we can still have symbol choice, because that's fine. And symbol choice ultimately is going to be a U32. And we're going to stick all of that, and we're going to derive clone and copy. But we're not going to give EQ and partial EQ and so on. We are, however, going to write some implementations for that. So import symbol choice. Pub fn pub crate fn new, which takes a set size and gives back a self. We're not going to say new, we're going to say any. And size is going to be a U size, and we're going to assert. We're just going to assert size is less than 32. So the way that we're going to represent symbol choices is that if the top bit is set, it's resolved, and exactly one other bit must be set. If the top bit is not set, then it is not yet resolved, and 0 or more bits are set. Although, fairly obviously, we want at least one bit set, because if we get to 0 bits, then we've broken the puzzle. So this is going to be... So size is the number of symbols. And what we want is we want ones in that. So it's going to be a self of size of 1, shifted left size, -1. So if size is 6, which it will be in our case, we're going to shift 1 left 6 places, and then we're going to subtract 1. So we're going to end up with 6 1-bits. And that means that we'll be able to initialize the board. So we're going to need a function, initial board, which comes from self and produces a board. And basically what we're going to do here is we're going to initialize the board, and then we're going to take, for every constraint that we have, a logical step. Although we'll do logical steps separately. So an initial board is just give me all the cells with all their valid values. So there we go. So this is going to be let mute ret equal board empty, and import board fn empty. So we're going to do that. And then what we're going to do is we're going to... No, we need to tell it how many... So we're going to go board empty, and empty is going to take the number of cells. So that's going to be self.cells.len and the number of and the symbol sets. Borrow self.symbols. So we're going to take n cells, and we're going to take that. Now we're going to go cells is vec with capacity n cells times symbols.len. And I'm going to go for cell in zero to n cells for symbols in symbols. Cells.push symbol choice any symbols dot size or dot len. Okay, so now we just need in symbol set, we need len function. And we can implement index for type output will be a symbol. And it's going to be self dot that. That needs to be mutable. So back to creating an empty board. Okay. Next step is we need to be able to print a board. Pub fn print board. So we need, I mean, in theory, the board ought to know which puzzle it came from. If the board knows the puzzle it came from, we'd start having to have all sorts of complicated wrappers. I'll worry about that later. So for now, we'll just assert equal self.cells.len times self.symbols.len board.cells.len. So we want to know minimum row, minimum column, maximum row, maximum column. I mean, at the moment, we're only doing 6x6, so we could be really dodgy, but I don't want to do that because I'd rather keep the print board function to work for later. So let's do this by saying that for So we're just going to get the minimum and maximum rows and columns, which in theory we could have stored into the grid anyway. But we only need it during this kind of printout. So let's not worry too much about doing this. Now we're going to say for k in self.row cols.keys, and it's not going to be k, it's going to be row and column. Min row equals min row dot min row. Min col equals min col dot min col. Max row equals max row dot max row. Max col equals max col dot max col. So that's got us our minimum and maximum rows and columns. We now need to work out what the maximum width is of a cell. And that is the sum of the symbol set widths. So let cell width equal self.symbols dot iter map given ss.width dot sum. And now we need to know what the width of a symbol set is. Pub fn width self usize, and it's going to be self.symbols.map symbol width dot max. And now we need an implementation for symbol, which probably is only going to be for the crate. Mismatched types, expected usize found enum option usize, unwrap or 0, because if there are no symbols then we can't exactly do anything with it. So now we have how wide the cell is, which is just the sum of all the symbols. And so now what we can do is we can print out, so for row in min row dot equals max row, for col in min col dot equals max col. If let some index, some cell is self dot get, self dot row cols dot get row col, can I do it dot as deref? That doesn't deref it. That's really annoying. Dot copied. There we go. So it's got us our cell index. And now what we want to say is we want to know the symbol sets, or the choices, sorry, in the board for that cell index. So for choice, sorry, for I comma choice in board dot choices cell dot enumerate. So choices takes a self and gives back an impl iterator item equals symbol choice. And it's going to be, that takes a cell index. And what we know about cell indexes is that they're just usizes. What we don't know is how many symbol sets there were. So let's make sure the board carries that information, because that's cheap to copy anyway. So we're going to have n cells and we're going to have n symbols, just because it'll make the maths easier. And so let's have a look. We want to find the cell choices for cell index. So what we know is that there are n symbols entries. So we want index times n symbols will give us the index into cells. So let idx equals idx dot 0 times self dot n symbols. And we're going to assert that index plus self.n symbols is less than the length of the vector. So that just ensures that we've been handed a valid index. And then what we're going to do is we're going to go self.cells dot iter dot skip index dot take n symbols dot copied. And it's going to tell us something about hidden type for blah captures a lifetime that does not appear. So we add our thing that says this is using self to achieve that. So we now have a symbol choice and a row. So if let some value equals choice dot single value. So in this particular instance, we have value is the symbol in the set that we want. So symbol equals self dot symbols set value. And that would be that. And that's not going to work because choice doesn't have single value. So let's come back and have a look at symbol choice. Option usize. So what single value is going to do is if self is only one value, we will return it. Otherwise, we will return none. And so the way that we can do that is we can say that we don't care about how many values there are. We can go values is self dot 0 and self value mask, and let's add some constants to impulse simple choice. Pub const value mask which is going to be 1 shifted left 31 minus 1. And these are in fact not public because they're only going to be used internally. So what we want to know now is that there's only one set bit. So if values dot count ones is 1, sum values dot I just want the index of the set bit. How do I get that? So there's no log 2 on U32. Let's have a look and see if we can find something. So the U32 type, what can we find out? Checked ilog2. Ooh, returns the base 2 logarithm of the number rounded down. Returns none if the number is 0. That might be a nice way to do it, actually. Checked ilog2. So actually we can go values.checked ilog2. So the log 2 of a number should be the index of that one set bit. So that's going to be, we still want if values.count ones is 1, else none. That should work. Is there an ilog2 without the check? We'll panic if it's 0. That's fine. And then we don't need the map. We can just do an as use size and stick the whole lot in a sum. So let's go back to the puzzle. Where are we now? Cannot find value choice in this scope. Not found in this scope. What have I fluffed that up completely? File contains an unclosed delimiter. For that. There we go. Right. Okay. So if there's a single value set for this choice, we have it. Else we need to print a blank for the symbol set. So cell width is the whole width, but we know the symbol set because it's self.symbols set. So we just need to print that many spaces. For we're just going to do this hideously inefficiently. So now symbol doesn't implement display, but we can fix that very easily. For your symbol. And it's just going to be self.display.format F. Because we're just showing the display name. And I want to rename that display to display name because I think that's not good. But I'm just going to call that name. Right. So, for each choice, we do that. We can then print a space. We want to print spaces between the choices, and would we want to print commas between the choices, or do we not care? We don't care. We're just going to print that. We'll print a question mark if we don't know what it is. Else. Right. How do I... I'll give it some critical format args. The format shows us. Okay, so how do I specify the width of something? Here. So it's colon width. So I can print colon cell width. That. Might the dollar there? Yeah. And then there I can print learn. Okay. Woof. Well, that was a lot of code for no good reason. So let's stop debug printing the puzzle. Let's get a board, which is going to be puzzle.initialBoard. And let's do puzzle.printBoard. Board. So what that should print basically is a 6x6 grid of question marks. We panicked. Joy. We got 1, 2, 3, 4, 5 rows. 1, 2, 3, 4, 5 in, and then we panicked. So we panicked on the last cell. That suggests our initializer for the board isn't quite right. Let's debug print the board. Board can't be debug printed, but we can trivially fix that. Except symbol choice can't be debug printed, but we can trivially fix that. So we said we had 36 cells, which is true for a 6x6. Index plus self.end symbols. Oh, it's not less than, it's going to be less than or equal to. Because it will be equal to the length the moment we get to the last symbol. There we go. Right. Ui, ay caramba. So we have the board, and the board has nothing in it. So our next step is going to be to gain some constraints and those constraints are going to be given digits. So we're going to write a given digit constraint. So we've got constraints, and we're going to have mod given digit. Okay, and we're going to have struct given digits, which is going to contain a set of row, column, digit. For now. And this is going to take an import, so it's going to take a givens, which is going to be a borrow, usize, because I really can't be bothered to be clever at this point, and it's going to give back a self, and that's going to be self is givens dot to vec. And we are going to pub use given digit. And that's going to be pub constraint is that, and I'm going to make that fully pub. So now in main, we, having constructed the puzzle, we need to give it some constraints, and those constraints are going to be the given digits that we're going to give it. And so the way that we're going to achieve that is to create the given digit constraint with the given digits for our puzzle, add it to the puzzle, and then hopefully we can write something to do some logical steps. So the given digit constraint, so digits is going to be Kaji constraints given digits new, and we're going to give it the digits that we got from this puzzle here. So row 1 column 2 is 5. 1 2 5. Row 1 column 6 is 2. 1 6 2. 2 5 4. 3 3 1 3 4 2. So in theory, we could build these constraints by having some data structure or like some string representation, but at the moment, I don't want to think about that. So 4 3 5 4 4 3. 5 2 6. 6 1 4. And 6 5 3. So those are all of our given digits. Next, we're going to insert that constraint into the puzzle, which means that our puzzle is going to have to be mutable. And we're going to say puzzle add constraint digits. And that's going to fail because obviously puzzle doesn't have an add constraint. So let's write that. Pub fn add constraint. Which is going to be an impl. It's going to be a C. So add constraint C, which is a constraint. Oh, goodness me. Right. Okay. So what we want to do at this point is we want to say self dot constraints dot push box new constraint. And then having pushed the constraint on, do we need to do anything with it? We should ask the constraint to initialize against the board. Is that fair? Or we can ask the constraint to add initial work. Well, at the moment we don't know anything about that. Parameter type C may not live long enough. The parameter type C must be valid for the static lifetime. Why? We've passed ownership of the type in. Oh, so by saying tick static, we're saying that there's no referencing in there. That's fair. So this is now going to tell us that given digits doesn't implement constraint. That's fine. Import constraint for given digits. Currently there's nothing to do except that given digits has to implement debug. We can do that. And we're back to where we were. So we've done that. We've added the constraints. We've asked for an initial board. Is it fair to say that an initial board should have one logical step run? No, the initial board is empty. Then the first time we run the... No. So there's going to be a setup, and setup is going to be called on every constraint for the initial board. Yes, I like that. So let's add what that looks like. So there's going to be an fn setup, which takes a borrow self. Or does it take a borrow mute self? I'm going to let it take a borrow mute self. No. No, because setting up might add inferences. I'm going to call it prep board. Prep board takes borrow self. And it takes a board. And it takes a... Is it fair to say that it takes a puzzle and a board? Why not? So, puzzle is public, board is public, puzzle is pub crate. So that's import crate puzzle board, and we can just stick puzzle in there. So we've said that to prepare a board, we do that. So what does prepare a board mean? Prepare a board ready for playing. This step, this is called exactly once and is used to apply constraint information to the initial board created during solving. Yeah, I think that's fair. if the constraint has no preparation to do, this can be omitted. However, if omitted, the constraint must provide a logical step. And we'll worry about the fact that prepboard really ought to have a way to signal that there was a problem later, but we're fine for now. So the given digit constraint is going to implement prepboard. And we're going to replace qualified path with use. Replace qualified path with use. I don't like the re-export behavior. There we go. Right. Okay, so given digit constraints, just attempt to restrict the digits in sequence into the board. So what we are going to say is we're going to say we're only going to use the first symbol set. Do we have a symbol set index? I don't think we get a symbol set index. Symbols, symbol ID, symbol sets to IDs. So I think we need a way to ask the puzzle for a symbol set. So pub fn symbol set, taking self and an index. Symbol set self.symbols index. So now we can get a symbol set out of the puzzle. We can say that we want to go so for row column digit in self dot digits. We need to get the cell at that row and column. So let's cell equal puzzle dot cell at row col. We're going to have to write that function as well. And that's going to return an option cell index, and it's going to be self.row calls. Get that dot copied. So if let some cell equals that. So we now have a cell index. We need to get the symbol index. So we're going to say let digit equal puzzle dot symbol set 0 dot square bracket dot 2 IDs. I don't like all of that. So what we're going to have is we're going to have pub fn symbols. Item equals symbol ID. So self.symbols set to IDs set. Right, let digits equals puzzle dot symbols and set 0 dot to vec. No method to vec for opaque type blah. So dot collect vec. So we have the digits. Assert that digit is less than or equal to digits.len. And assert that digit is greater than 0. And now we want to set that symbol. So we're going to go puzzle.set symbol board cell digits digit -1. Pub fn set symbol self cell index symbol ID board I think we're going to end up wrapping board slightly to make this a little bit less unpleasant for passing stuff around, but it'll continue to be fine for now. Okay. So the first thing that we need to do is we need to work out the cell choice for that symbol ID in that board. And to do that, we need to decompose the symbol ID into its symbol set and symbol index. So symbols, symbol ID. We're going to have impl dref for symbol ID. And target type for dref. Oh, dref gives you a borrow. That's not what I want. I actually just want to. So we're going to go fn 2 parts into parts, which takes a self and returns a usize. And it just is going to return the set and the symbol. So it's going to be self shifted right 5, comma, self and 31. So what's wrong with set symbol? No method name set symbol found on borrow puzzle. Okay, right, that's gone away. So now what we need to do is we need to go let set comma symbol equals symbol into parts. Into parts is private. It won't be. It will belong to the crate. So we now need to get the choice for that cell. So let choice equal board dot choice cell set. Actually, should I give it the simple ID and let it extract it? Yes. Okay. So choice IDX is 0 times self.in symbols plus symbol dot into parts dot 0. Okay, so that's choice, except we actually need choice mute. So let's repeat that as choice mute, which takes a borrow mute self and returns a borrow mute symbol choice. So at this point, we're holding on to the board. Cannot borrow board as mutable. Well, clearly we need to be able to, if we're going to be able to write to it. So we need to be able to fail, I think. So let's have, well, we're just going to assert for now if we can't. So let's go assert. So let's get the symbol and symbol number out, because we should. We've got the choice. We need to determine whether or not the board is able to have that value at that position. So assert choice dot can be symbol number. And let's continue on to implementing that. So pub fn can be so we can be that symbol if there is a 1 in that position. So that's self dot 0 and 1 shifted left symbol is not 0. Simple. So having asserted that it can be that, we should set it to be that. So that's going to be choice dot set symbol number, fn set and that then means that self.0 is solved mask or one shifted left symbol. Right, and having set that choice, we need to propagate the result of that cell using the implications. So now it's going to be self.propagate changes board cell. Propagate changes takes a self, a board, and a cell. And now we propagate what we know about the board. So what we do is, for now, if the cell is solved, we perform eliminations. That's the only thing we're going to do. So that's going to go if let some value equals board.choice for set in oh, no, dear gods, what am I trying to say? Right, so for each set we look and see whether or not the board at that cell index for that set is solved. If let some value, some symbol, is board dot choice set cell set dot single value so this is similar to before. It's idx.0 times self.end symbols plus set self.cells idx. And we'll almost certainly need a one for the mute later. So if that symbol in that set is set, we now need to propagate based on that. I've just realized that we've used a hash map where realistically we need a multi-map. Because it's that. Oh, do we? Yes. Yes, we need a multi-map. That goes to vec. Like that. It's not self.implications.insert blah. It's self.implications.entry blah dot or default push that. That's better. Okay. Where was I? Applying the implications. Oh, we never did the corollary actually. So while we're here, we're going to say let mut e equals that, e dot push that, e dot push. Oh, stupid me. I need to put the other implication in, which is that cell 1 lacks means cell 0 has. Can't happen. There we go. Right. Good job we spotted that. Okay. So, at this point, we know that the cell at cell index has symbol in set. Wow. I mean, that sounds ridiculous, but there we go. So symbol is symbol ID. How can I get the symbol ID? Assert I mean, this is hideous, but we'll get better APIs later. So we now have a symbol ID and we have a cell index, so we can apply the inferences. For inference, so for inference in self dot implications dot get cell symbol so at this point the inference is a vec dot flatten let's just be slightly more tidy about that. So instead we will say inferences is that. That's an option. So we're going to say if let some implications is that for implication in implications. So we have a cell ID, symbol ID pair. So actually for cell lacks for other cell lacks. We now need to knock lacks out of the other cell. So we can say board dot choice mute of other cell lax dot unset lax dot into parts dot one. So now we did an unset on symbol choice. Pub fn unset mute self symbol usize self.0 equals self.0 and not one shifted left symbol. Manual implication of that. There we go. Okay. Whew. Right, so propagating changes. Applies all the implications. Now, eventually, again, if we can't propagate a change for whatever reason, we should return an error. But for now, it will do. So we've written our prep board function, which calls set symbol. We've got all the way through that. Now what we need to do is call prep board for all the constraints that are registered to the puzzle when we create the initial board. So we need to say let mute ret equals that. In fact, let's call that board. And we're going to return board here. And we're going to go for constraint in self dot constraints constraint dot prep board self borrow mute board. Right, that should have settled things down. So at this point, what we should be able to do is cargo run and see the puzzle that we had before. So we can see 5 and 2 in row 1. Let's just double check that. Yep. 4. Yep. 1, 2, 5, 3. Yep. 6, 4, 3. Okay. So setting the puzzle up in the first place is clean. What would be nice to know at this point is what's left in the grid. So let's dump the board as debug as well. And if we do that, then we get to see a whole bunch of symbol choices, and those are solved. But what we're looking for is any symbol choice that looks like it has a power of 2, but isn't marked as solved. Because if we've got one of those, then we have what's called a naked single. So a quick look tells us that we do not have one, as far as I can tell. 36 is not a power of 2, 12 is not a power of 2, 48 is not a power of 2, 10, 33, 41, 23, 6. Ah, we do. There is a power of 2 symbol choice. And what that is it's telling us that effectively we have a single symbol that we need to work with, but that we've not marked as solved yet. And since we've not marked it as solved, we haven't applied its implications. So let's just try doing that. So let's write a new constraint, which we're going to call naked single. So I'm going to write mod singles. I'm going to create that module. We're going to have pub struct naked single. Now it doesn't need any data because naked singles just look at the cells in a board. So all we're going to care about is for each cell in the board, if it's not solved and it's single, set it. And that's going to be our logical step. So let's do that. So we're going to impl constraint for naked single. And we're going to register that constraint. So we're going to pub use singles naked single. In main here, having added the digits constraint, we are going to add Kaji constraints naked single. Naked single doesn't implement debug, so derive debug. We're back to good. So now we need to be able to support a logical step. So let's write the logical step. Execute a single logical step on the board. This may involve more than one action, but each action should be fully applied before trying to apply more. Is that fair, or should we say we should restrict ourselves to one action? Let's restrict a single logical action on the board. So this is going to be fn logical step, which takes a self, a puzzle, a board. If the constraint has no logical steps that it can make, then this can be omitted, but the constraint should implement board preparation instead. If the constraint could perform a logical action but is unable to given the current board state, it should return logical step no action. If everything the constraint could do has been done, it should return logical step finished. So in the future, we're going to have this logical, well, we're going to have this logical step enum now. Pub enum logical step. And this is going to be the result of running a logical step in our solver. Nothing was able to be done, no action. Nothing more is possible. Finished. And that should return a logical step. And it's going to return logical step no action. In fact, it will return finished on the basis that that way, in theory, in future, we could optimize and say, if the logical step function returns finished, we'll never call that constraint again. The other thing that logical step can do is have performed some action on some set of cells. So it's going to be acted, and for now, we'll just stick a string in there because, well, that will do. So in our naked singles, we are going to implement logical step. So let's pull puzzle and board in. And let's pull logical step in. Okay, so we said that naked singles are where for a given symbol set, for a given cell in the board, it is not solved, but there is only one symbol that it can be. So let's look at how we're going to implement that. We need to be able to ask for all of the cell indexes for the puzzle. So, do we have a cells? So we have a cell at, but we don't have all cells. So let's get an all cells. Pub fn all cells. Taking self will return an impl iterator item equals cell index. And this can literally be 0 to self.cells.len.map cell index. So we know that we can get all the cells. So we can say for cell in puzzle.all cells. We now want to say for each symbol set, can I please see the choice? How are we going to do that? For set. Oh, okay, no. Because naked singles really only make sense for the digits. And the digits are always going to be the first set. So we're always going to be dealing with set 0. So let's not even worry about that. What we're going to do is we're going to ask the board for the digits at set 0. Because naked singles, yeah, because if you have a hybrid puzzle, and well, I don't know, no, if you have a hybrid puzzle and there's only one symbol that the thing can be, it must be that symbol. So let's do that. Let's say for set in puzzle dot symbol sets so puzzle pub fn symbol sets self is going to give an impl iterator item equals usize, and it's going to be 0 to self.symbols.len. I don't like the usize, but you know, we'll deal with it. Come back to singles. So we now have that. If we manage to make it all the way to the end here without doing anything, then it's a logical step finished. No, it's a logical step, no action. Because frankly, we're only finished when everything is filled, and at that point we finish the logical solve anyway. So now we need to get the choice for the board. So let choice equals choice equals board dot. Okay. Time for the board functions to become public where appropriate. So that can become public. There's no reason that couldn't be. I don't want you to change choices in this way, though. So, choices set. No. Choices cell dot nth set unwrap. Okay, so we have our symbol choice, and what we want to know is if it's not solved, but it's singular. So let's have a test for that. So we've got single value, which just checks that it is a single value. So we can have pub fn solved, which just goes self.0 and self solved mask is not 0. If choice dot solved, if not choice dot solved and choice dot single value, if not solved, if let some value equals choice dot single value, so we are not solved and there's only one thing we can be. We need to say puzzle dot set symbol board cell puzzle dot symbol set dot id set value. Return logical step action acted format naked single the cell value at cell. Let cell equal puzzle dot. Okay. Cell name cell. Puzzle. Let's do cell info, which is going to return a cell info. And what does one do to format cell information? Where is cell info? It's there. It has a name. So if we import display for cell info, that's probably our best bet. Stick this at the end for now. Right, so display for cell is just the cell's name. Okay. Can stick underscore puzzle and underscore board there because we don't use them. And we can stick underscore puzzle and underscore board there because we don't use them. Right. Now we need to write the logical solver, which either gets stuck because no action was taken at all, or completes the board. And we can have a board.isSolved to check that. So we have an empty, and we can have a pub fn solved, which is just self.cells.iter.all given c dot solved. And now our logical pub fn logical step self board so all we know when we run a single logical step is that we run through all of the constraints trying to get a logical step, and if none of them act, then we return no action. And if all of them finished, then we return finished, because there's nothing more we can do. Yep. So let mute acted, well, no, let mute finished equals true for constraint in self dot constraint. Match constraint dot logical step self board. So no action does nothing. So no action says finished is false. Finished does nothing, and logic, everything else goes to return that. If finished, logical step finished, else logical step no action. Okay, if finished or board dot solved. Finished. Otherwise, no action. Right. So that's a single logical step. So now we can just do solve, which should return an option board. Well, return a board. So let mute board equals self dot initial board. Loop match self dot logical step finished return board. No action, nothing. So if we got all the way through all the logical steps and there was no action, but we're not finished, then println failed to solve. Break. Finished. Println finished. Break. Board. instead of saying act equals true, we're just going to dump out the action for now. Finally, rather than getting a board and printing the board out, we're going to go puzzle solve. Print board. Well, so we failed to solve because we just had naked singles. Well, we had some naked singles, but then we couldn't actually complete the puzzle. That's okay. That doesn't surprise me. What can I see? Completely off the top of my head, I can't see any other naked singles. So what we might have now are hidden singles. So let's try and do hidden singles because, again, it's a fairly simple constraint to implement. And after that, we're going to give up and call it a date because it's been a while. So again, a hidden single doesn't need any context. And its logical step needs the puzzle and the board. And what we're going to do is we're going to be slightly different here. This time, what we're going to look for is we're going to look for a region in which only one of the cells can have a particular digit for a given set. So we're going to go for each symbol set. So for set in puzzle dot symbol sets, for region in puzzle dot regions, let cells equals puzzle dot region dot to cells. So that's created the set of cells in that region. I suppose we should do the set inside because that's going to be slightly less hassly. Logical step, no action. So what we want to do is for this set, we want to find out for each digit which cells could, well, for each symbol, which cells could have that symbol. And there's one of three states. There could be none, which realistically is a problem, one cell, or many cells. So what we can do is we don't really want to build complex data structures for this, so let's have an enum. Let's go enum symbol state unknown single many use symbol state star. So we want to know what state we're in. The set's length we can determine by asking the puzzle for the number of symbols. So let n symbols equals puzzle.symbol set dot len. Then we can go mute symbols equals a vector of unknown n symbols long. The single is going to carry a cell index. And now what we're going to do is we're going to say, okay, For each cell in the region, what symbols can it have by getting its choice? So for cell in cells.iter.copied, choice is board.choice for the cell for this symbol set. Choice set. And you're going to tell me that choice set is private, so let's fix that. It's going to become public. Derive clone, just to shut the vec thing up. Cell index is going to get imported, and we can keep going. Right. So for symbol number in choice dot options, right, we need to implement that. So symbol choice pub fn options takes self and returns an option iter, and that's going to be an option iter mask is self.0 and self value mask. So pub struct option iter mask u32. Import iterator for option iter. Type item is usize. If self.mask is 0, none. Else ret is self.mask dot first set bit. How do I get a first set bit from u32? Leading zeros would tell us how many zeros there are. If that equals 32, then we're done. So we could actually just go match self.mask.leading zeros. 32, none. N goes to something else. So if there is one leading zero, then bit 30 is set. If there are 31 leading zeros, bit 1 is set. Sorry, bit 0 is set. So we want 31 minus n is the bit that is set. So let idx equal that self.mask and equals not one shifted left idx sum idx. I mean, it's not ideal. It will always we'll always go 9, 8, 7, 6, 5, 4, 3, 2, 1 kind of thing, but it's fine. Okay, Back to the constraint. So we don't have a symbol number. So what comes next is that we need to store, we need to mutate symbols at symbol number. So match symbols symbol number. Unknown. Becomes single cell. Single some cell or many become many. Right. At this point, if one of symbols is single, then I'm gonna label that tick cells, and I'm gonna say if board.choice, if choice.solved continue cells. There's no point in knowing the naked singles. Okay, for symbol in symbols. Match symbol. Single cell goes to something, everything else goes to nothing. So if there is a single, then we know that this region has a hidden single. So we can go puzzle.set for idx symbol in symbols dot into iter dot enumerate. So step one, we need to build a symbol ID. Let symbol equals puzzle dot symbol set dot id set symbol puzzle dot set symbol return logical step acted hidden single that doesn't naked single 0 at row 6 column 2 is actually that 1, so we need to fix that as well. So let's stick that to do in there just because otherwise I'm going to get worried. Let's come up here and fix the naked single first. Let's see if that's better. Let's get this right. So let value equals puzzle.symbol set index. Let region equals puzzle.region region dot let cell puzzle.cell info cell hidden single value at cell in region. Now you're going to tell me that regions don't implement display. So we're going to import display for region self.name.format. We seem to be trying to use match for a singular if let. That's fair. So there's our logical step. So that failed to run with the naked singles. So let's now register hidden single as a constraint. Which of course requires that we use it. There we go. So there was a single hidden single, and then we could solve the rest of the puzzle with naked singles all the way to the end. And that gave us that puzzle. Which, let's have a look. 1, 2, 3, 4, 5, 6 in column 1. Row 3. Box 6. Yeah, I'm willing to believe that's right. So we have a logical solver that's capable of using naked and hidden singles on a 6x6 Sudoku. Next time, we'll try and make it more generic by teaching it some constraints for Sudoku boards so that we can build out those regions and so on at construction time. And then we'll see what we can do to add some other kinds of solving to the puzzle. So at this point, let's have a look at what we have. I'm just going to say, so initial solver with singles. At this point, we can construct a 6x6 Sudoku, classic Sudoku puzzle. We can give digits, and we can solve it so long as it only needs naked and hidden singles. And you'll notice that even if there were extra hidden singles, in theory, we did all the naked singles first, because we always take the first constraint. And I think in general, we're going to want to make sure that we put cheaper constraints before more expensive constraints in terms of the solving. And we may want to split constraints and logical steps. I don't know yet. We'll see. Because hidden singles and naked singles aren't really constraints, but terminology. We have that. Let's see if we can create a repository. We're going to put it on GitHub. The repository's name is going to be Kaji. It's going to be in my username. Description is going to be a logical puzzle solver. It's going to be public. git remote add origin. Okay, so in theory, if we go to there's no README or anything, but all of the source code is there. You're welcome to have a play around with it. I probably won't be accepting pull requests and so on at the moment. Although if someone wanted to do a GitHub Actions for checking it, then I wouldn't object massively. Next stream, we will carry on and, like I said, try to get the Sudoku solver to be a little bit more able to do larger grids and potentially other constraints. Thank you for watching.